Hello everyone, welcome to this lecture. So, in this lecture we will quickly do a security analysis for the BGW MPC protocol for linear functions, which we had discussed in the previous lecture. So, before going to the formal analysis, we try to understand that why this protocol is secure with an example here. So, let us consider a very simple function, namely the addition of 4 inputs here. We have 4 parties up to which we have 4 parties and up to 1 party can be corrupt. So, for simplicity, imagine that the first party is corrupt. Of course, the parties will not be knowing that it is the first party who is corrupt, but they will be knowing that up to 1 party can be corrupt here. Okay. And we will perform all the computations over the field Z5, where the plus operation is the addition modulo 5 operation and the multiplication operation is the multiplication modulo 5 operation. We fix the evaluation points which are going to be used during the instances of the VSS to be 1, 2, 3 and 4 for P1, P2, P3, P4 respectively. Now, suppose the inputs of the parties are 2, 1, 0, 2, 1, 1 and 0 respectively. So, during the input stage, suppose the sum is sharing polynomial through which x1 is shared is this polynomial A, which is 2 plus 0 z, and say at the end of the sharing phase protocol of the VSS scheme, the shares for the parties are 2, 2, 2 and 2 respectively. In parallel, suppose P2 in its instance of the secret sharing protocol, where VSS protocol uses the sum is sharing polynomial 1 plus 0 z, and say the resultant shares are 1, 1, 1, 1 respectively at the end of the sharing phase. In the same way, imagine that P3 during its instance of the VSS scheme has used this sum is sharing polynomial, resulting in the shares 3, 0 and 2 and 4, and P4 in its instance of the VSS scheme uses the polynomial 0 plus 3 z, resulting in the vector of shares 3, 1, 4, 2. So, all this VSS instances uses they use polynomials of degree 1 because t is equal to 1. Now, since there is only one linear gate, namely the addition of all the 4 inputs, each party will locally add the shares of x1, x2, x3, x4 to obtain the share of y. So, P1 will it is going to add all these 4 shares, and of course, the addition is performed modulo 5, that will result in P1's share to be 4. Okay. And in the same way, P2's share will be the addition of all these 4 values, P3's share will be the addition of these 4 shares, and P4's share will be the addition of these 4 shares. And now the output stage starts. So, since P1 is corrupt, it is supposed to make the share 4 public, but suppose it says that my share is 2, and that is fine because that is allowed because P1 is corrupt. So, it can deviate from the protocol instructions. So, it is supposed to make public the correct share of y, but it is making an incorrect share of y public. Okay. No one of course, will know whether P1 is corrupt or not. However, the other parties make correctly their shares public. Okay. So, P3 makes public the share 4, P4 makes the share public, and now the vector of shares corresponding to the output gate will be available with everyone, and now they will do the Reed-Solomon error correction and recover this 1 degree polynomial, and the output will be y equal to 4. That is a possible execution for the BGW protocol. Now, let us see that whether the privacy property holds here or not. That means, whether the adversary learns anything additional about the inputs of the honest parties beyond what it is allowed to learn. So, in this table I have highlighted the view of the adversary in bold. What does the view mean? View means whatever information the adversary learns through the corrupt parties. So, in this case P1 is the only corrupt party. So, the adversary's view will be consisting of the input of the party P1 and all the shares corresponding to this input T generated during the VSS instance, where P1 is the dealer. However, for the remaining 3 VSS instances, the view of the adversary will be independent of what exactly are the secrets in those VSS instances. So, that is why x2 is unknown for the adversary, x3 is unknown for the adversary, x4 is unknown for the adversary. Adversary will have only its share from those VSS instances, and of course, it will not know what shares the honest parties have received in those VSS instances from the corresponding dealers. And now, during the reconstruction stage, everyone has made public their respective shares of the output value. Okay. Of course, P1 has made public the incorrect share, and then the Reed-Solomon error correction has resulted in the output y equal to 4. That is the view of the adversary. Now, this view adversary can try to analyze to see whether it can learn anything additional about x2, x3, x4. Of course, adversary will learn. Okay, by the way, I have filled this table now. I have filled this table with the values which are been used by the parties during the execution of the protocol in our current example. Okay. Now, this x2, x3, x4, they are currently unknown for the adversary. So, adversary based on its own input 2 and the function output y equal to 4 can make many hypotheses. It knows that the function which is getting computed is the sum of x1, x2, x3 and x4. Out of that, x1 is known, x and the sum y is also known. So, it can always conclude that there are various possibilities for x2, x3, x4. So, for instance, one possibility could be that P2 has executed the protocol with input 2 and P3 has executed the protocol with input 0 and P4 has executed the protocol with input 0. That is quite a possibility, okay, because if indeed x2 is 2 and x3 is 0 and x4 is 0, and if P1's input would have been 2, then together it will result in the function output to be y equal to 4. Now, what adversary can try to do is the following. This table right now is unknown for the adversary, namely the values in red color, and adversary is suppose making an hypothesis. Then is it possible that I have participated in the protocol execution where x2 was 2, x3 was 0, x4 was 0, and the values in bold in this table are the values which I have seen. And indeed, it is quite possible that P2 has participated in the protocol with x2 equal to 2 and P3 has participated with input x3 equal to 0 and P4 has participated with input x4 equal to 0. More specifically, if P2 would have used the polynomial 2 plus 4z in an instance of the BGW protocol for linear function, then it would have resulted in P1 getting the share 1. Of course, P2, P3, P4 might get other shares, but P1 is not going to see what exactly are the shares which 2, 3 and 4 have received in that instance. And in the same way, it could be possible that P3's input during the run of the BGW protocol was 0 and it has used the sharing polynomial 0 plus 3z, which would have resulted in the share 3 for P1. And similarly, it could be possible that P4's input was 0, its sharing polynomial was 0 plus 3z, which would have resulted in P1 getting the share 3 during a run of BGW protocol. And now, you can see that magically it is so happening here that if the BGW protocol would have been executed with x2 being 2 and P2's sharing polynomial being 2 plus 4z, x3 being 0 and P3's sharing polynomial being 0 plus 3z and x4 being 0 and P4's polynomial being 0 plus 3z, along with P1's input being 2 and its sharing polynomial being whatever it has used, then that completely matches with all the information which actually P1 has received during the run of the protocol. As a result of that, adversary cannot simply rule out this possibility. So, what I am trying to argue here is that even though the protocol was executed with inputs being 2, 1, 1 and 0, whatever value adversary namely P1 has seen in that run could have also resulted if the BGW protocol would have been executed with input x1 being 2 and input x2 being 2 and inputs x3 and x4 being 0. Now, there are other possibilities as well, which along with the input x1 being 2 can result to the sum 4. For example, one possibility could be that x2 was 1, x3 was 1 and x4 was 0. Let us see whether this possibility could also result in the same set of values, whether this possibility matches whatever adversary P1 has got during the run of the protocol. And indeed, it is quite possible that P2's input was 1 and its sharing polynomial was 1, P3's input was 1, its sharing polynomial was 1 plus 2z, P4's input was 0, its sharing polynomial was 3z, and along with that P1's input was 2 and its sharing polynomial is whatever it has used, and altogether it leads to a scenario where the values learnt or seen by P1 during the run of the protocol matches. Okay. That means adversary again cannot rule out this possibility, and in the same way adversary cannot rule out the possibility of x2 being 0, x3 being 2 and x4 being 0, because indeed it could be the case that P2 has participated in the BGW protocol with its input being 0 and sharing polynomial being z, P3 has participated with input being 2 and sharing polynomial being z plus 2, and P4 has participated with input 0 and sharing polynomial being 3z. Of course, due to lack of space in this slide, I cannot show you the other possibilities, but you can work out and you can see that magically what is happening here is that whatever is the adversary's view, namely the first table which it has collected, and when I say the first table I mean to say with this question marks here, because all those things were unknown for the adversary. Okay. That view is going to be consistent with every candidate x2, x3, x4 from the field Z5, such that candidate x2, x3, x4 along with x1 being 2 leads to the value 4, and that is why adversary cannot pinpoint what exactly were the values of x2, x3 and x4. Now, let us try to understand that why this is working. For example, it is fine, but we have to give a general argument that why the adversary will fail to identify anything about the inputs of the honest parties. So, where exactly is communication happening in the protocol? The communication is happening during the input stage and during the output stage. So, let us first fix the set of corrupt parties to the set C. We have to T corrupt parties here. So, during the sharing phase, during the input stage corresponding to every honest party Pi, how much information adversary learns? Adversary learns up to T shares, but we can use the privacy property of the underlying verifiable secret sharing, which guarantees that the probability distribution of the T shares which adversary sees corresponding to the inputs of the honest parties is independent of the actual input, which is secret shared. So, whatever T shares the adversaries sees corresponding to the inputs xi of the honest parties, that does not help the adversary to find out anything about xi. Xi could be any random element from the field. During the computation stage, no interaction happens among the parties. So, whatever adversary has learned from the input stage, it has learned the same amount of information even at the end of the computation stage. And now you have the reconstruction phase or the output stage basically, where the parties publicly reconstruct the function output, and here adversary learns some information. Learns means it receives some messages from the honest parties. What are the messages, what are the values it receives from the honest parties? It receives basically the shares of the output value from the honest parties. Of course, the adversary has up to T shares correspond of T shares of the output value y corresponding to the corrupt parties. But now the interesting thing is that these shares corresponding to the value y received from the honest parties, they are not going to add anything additional to adversary's view. It is not going to provide any new information to the adversary, because adversary already has the knowledge of the function output y, because that is anyhow going to be learned or allowed to be learned by everyone publicly, including the adversary. And adversary itself has the T shares corresponding to T shares of the output y, to be more specific, T shares of the output y corresponding to the corrupt parties. That means, it has the point 0 y and it has the points alpha j y j corresponding to every corrupt parties. Now, using so how many points total he has now? He has total t plus 1 points. Now, using this t plus 1 points, it can completely identify the output polynomial which it is going to see at the end of the Reed-Solomon error correction process, because this t plus 1 points uniquely define that polynomial which is going to be obtained at the end of the Reed-Solomon error correction process. Call that polynomial as say f sub y z polynomial. Now, this f sub y z polynomial automatically defines the y shares for the value y corresponding to the honest parties, because those shares are nothing but the value of this f sub y polynomial at alpha I corresponding to every honest party p I, and that those are the precise shares which adversary is going to receive from the honest parties during the output stage. But at the first place he already know those shares. That means, it already knows that I am going to receive those shares from the honest parties. So, it does not add any new information to adversary's view. That means, whatever shares it is going to see, which is going to receive from the honest parties as part of the output stage, it could have computed, pre-computed before itself without even waiting to see what the honest parties are sending to him. And that means that this information, this exchange of information during the output stage is nothing, it is not going to add anything new to adversary's views, and that is why we can say that adversary's view is simply limited to T shares corresponding to the inputs of the honest parties as far as the inputs of the honest parties are concerned. But anyhow, the probability distribution of those shares is independent of the actual inputs secret shared by those honest dealers, and that ensures the privacy property. Okay. Now, let us see the correctness property. So, our claim here is that at the end of the protocol every honest party will obtain the output y even if up to t corrupt parties behave maliciously. So, again let us fix the set of corrupt parties to C, and during the input stage what is going to happen? If there is an honest party p I, then even if the corrupt parties misbehave during the secret sharing instances of those VSS instances, during the sharing phase protocol of those VSS instances, the correctness property guarantees that at the end of the sharing phase instances of those VSS schemes, the input xi is NT sum is shared. That means, there will be a t degree polynomial with xi being the constant term and every party having a share on those polynomial. However, if the party pi who is acting as the dealer in some secret sharing instance of the VSS scheme is corrupt, even for such corrupt dealers the strong commitment property of the underlying secret sharing scheme guarantees that some input xi is secret shared, some is shared on the behalf of pi. That means, it is not the case that corresponding to the corrupt parties no value is secret shared in an NT sum is shared fashion. The strong commitment property guarantees that some value is indeed secret shared on the behalf of even potentially corrupt parties in the system. That means, at the end of the input stage all the values for respective parties are secret shared. On the behalf of the honest parties xi will be secret shared, even on the behalf of corrupt parties some value are NT secret shared. Now, the computation stage involves no interaction. So, what we can conclude is that at the end of the computation phase the value y, which is defined here, is NT secret shared, and now during the reconstruction phase every party makes public its share of the output y. Up to t corrupt parties make public incorrect shares, but we are working in the setting t less than n over 3 and this value y is secret shared through a t degree polynomial. It is secret shared through t degree polynomial. So, we can now apply the properties of Reed-Solomon error correction, which guarantee that even there are up to t shares which are incorrect in this vector of shares for the value y, the Reed-Solomon error correction algorithm will identify what are those incorrect shares and give you back the correct output y, which guarantees that even if there are up to t corrupt parties who behave maliciously in the protocol, the honest parties end up obtaining the correct output y. Again, my analysis and explanation here for the privacy and the correctness properties are slightly loose because there are a bunch of other properties also which we might expect from any generic MPC protocol, but we can prove that even those properties can also be achieved by the BGW protocol here. If you want to know more about the full rigorous analysis of the BGW protocol, you are strongly encouraged to read the first reference here. Thank you.